Is this thing on? Okay, we're good. Okay, so here we are, Chapter 2C, the last of Chapter 2 you're ever going to deal with. To see or not to see? That's the question. Oh, come on, open your eyes. It's a joke! All right. We got to talk about the states of matter and the kinetic molecular theory. That is kind of an important idea in chem. And well, what do we mean by kinetic molecular theory? Well, let's break down the words here. One, it's a theory, which means it doesn't explain everything away. We're still working on it. Number two, molecular. That means it might be involving particles. It might be involving things like molecules and atoms and all that. And then what's kinetic? Well, you know, we talked about that earlier in like the first video where we talked about kinetic being moving. It's like King Julian, you know, on the Penguins of Madagascar. I'm moving. Yeah, it's King Julian is like kinetic. A lot of movement. So when we look at movement with molecules or atoms, and it's a theory, we're trying to understand in these different states of matter, how do the particles behave? How do they act? Are they going, woo, party, yeah, bring down the house, yo? Or are they more like mellow? Now we know they don't stand absolutely still. They don't, because we have not reached absolute zero. Not yet. Okay? I have a feeling they do reach absolute zero. See the last video. The apocalypse might possibly come. Maybe. I leave that one up to God. That's his call, not mine. But let's take a look at what's happening. So we'll look at solids. And particles, attractive forces. Well, what do we mean by attractive forces? Well, particles do have an attraction for each other. Now, sometimes it can be a lot of attraction, sometimes, not so much. But it is greater than the kinetic energy between the particles. Now remember, everything's got kinetic energy in it. But if the attractive forces are greater than the kinetic energy between the particles, then they are much more likely to come together and stay together. Okay? So that's in the solid. So in other words, the attractions are greater than the kinetic energy between the particles. Now, the particles are in relatively fixed positions with set distances between them. In other words, they're nice and neat and orderly. They don't move very much. There's not a lot of energy to it, and the attraction is greater than the kinetic energy that they have. Now, in a liquid, there is a little bit more kinetic energy in there. Particles partially overcome the attractive forces between them. Partially overcome. So it's not quite the same. They're still together, but they're a little bit more apart. There's a little bit more, you know, movement, a little bit more, okay, cha-cha-cha. So particles can move about but remain close to each other. That's true about liquids. We can, you know, have a liquid slip and slide on the table there or whatnot. Or think about if you've ever had slip and slide in your backyard on a hot summer day. Oh, those are awesome times, yeah. Okay, why is it possible for us to be able to slip and slide on liquid water as opposed to, you know, ice cubes, okay? Or even snow. It doesn't quite have the same thing. That's because the liquid's a little bit more flexible. It does move around a little bit more. What about gases? Well, gases, okay, we're talking about those attractive forces, they are overcome. And do you know why? Because the kinetic energy is a whole lot more than the attractive forces that there are there. Okay? And it is completely overcome. That's it. It's done, man. We are going. Particles possess a large amount of kinetic energy. Okay? Gases are highly compressible. Demo piece of paper. Oh, hey, that's a note for me, right? Okay, let me see if I can find a piece of paper. But while you're at it, take a look at that last statement there, because that is a fairly important thing that you're seeing there as I'm trying to find a piece of paper. Okay, nope, that's not it. Can't use that. Trying to find scrap paper, guys. Oh, here we go. I don't think this person's going to mind anymore. So, there's no definite shape. Gases don't take a definite shape. Whereas liquid, it'll take the shape of whatever container it is in. A solid, it's kind of obvious the kind of shape that they're going to take, right? But what about gases? Well, what do we mean when they're compressible? Well, if I were to go and crumble up this piece of paper that you're seeing here, I can still squeeze it down, can't I? I can squeeze it down. And the truth is, isn't that what we do with gases? How else do we fill our car tires? With this, right? Yeah, absolutely. So gases have to be compressible. That's what's happening in the real world. Real chem, real fast. Okay? No definite shape. As we are winding down our chapter, plasma. Don't get this confused with the plasma in the blood. No, 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 no. Two separate things, ladies and gentlemen. Plasma in chemistry refers to a state of matter where there is way more kinetic energy than you have in a gas state, because so much energy is absorbed, taken in, taken on by the atom, that some or all of its electrons are stripped away. Can you imagine electrons being stripped away? Ow! That's gotta hurt. Okay? That's like pulling your hair out. Too late. Okay, forming a positive ion. So that's the thing about plasma. Really hot. Now the funny part about this is, it is the most common state of matter in the visible universe. Not really common here on our planet, thank God, because I don't think we could handle that. Okay, so there's a lot of energy out there in the universe, without a doubt. So we've looked at the kinetic molecular theory. How is it that the particles behave? Remember, particles, it could be atoms, it could be molecules, it could be atoms and molecules combined together. Okay? And we know that when they're a solid, not a lot of kinetic energy, more attractive forces. In a liquid, there's more kinetic energy, but you still have attractive forces, but the liquids get to move around a little bit more. And then the gas is kind of like, I am free! Okay? I am free. And they have definitely more kinetic energy, less attractive forces, and then by the time the plasma comes in, free at last, yeah, woo! It's kind of like the last day of school. Oh wait, we just started the year. Oh. Oops, my bad. All right. Changes of common states of matter. Man, this is stuff you should know. This is Science 101. Condensation, gas to a liquid, vaporization, liquid to a gas, freezing, liquid to solid, melting, solid to liquid, sublimation, solid to a gas. Some people would say, wait a second, where do we see that happening? Dry ice. How else do you lose the dry ice? You never see liquid dry ice, do you? No, you don't. You've got dry ice and then it goes into a gas. That, boys and girls, is sublimation. And then we have deposition, gas to a solid. Yeah, that's it. Gas to a solid. Ooh, hey, how does that work? Well, we could look at weather. Think about water vapor going down maybe from cloud directly into hail. Yeah, maybe. All right, ladies and gentlemen, with that, we are done with Chapter 2. You got to experience 2C. You got to finish the last part of 2B. That is it for Chapter 2. Hope it benefited you. You guys, take care. Don't work too hard.